journey of, right now we're working on what? Accumulation from rate or rate from accumulation? We're on the backwards journey on rate from accumulation. Here's the, this is the function for, if this is the radius here, your x-coordinate is the radius of a sphere, this gives the volume of the sphere. Okay, so this is the 4/3 pi r cubed. 4/3 pi r cubed. So this is showing the volume of the sphere. And how could it be thought of as an accumulation function? So if I put in, say I put in 1.5, that gives me a y value of 14.1372, right there. So how can this be thought of as, so this just quantity function, volume of a sphere, how can it be thought of as accumulation?
Sphere with the radius of 1.5 units is going to have the volume of 14.1372 units.
Okay, that's true. He said a radius of volume 1.5 has a volume of 14.1372. Okay, but that doesn't bring in the idea of accumulation. How is this function thought of as accumulation?
As the radius increases, the volume increases.
So be more specific. Talk to me about this. How can this information be thought of in terms of accumulation? Autumn.
When there's a change in the x value of 1.5, then the y value accumulates by 14.1372 units.
Okay, so but it's very important that we say which change of 1.5. Because if you change it in a different place, a change of 1.5 is going to lead to a different accumulation. So which change of 1.5 units of radius? So what is that, which change? If x is 1.5, what change is that indicating? From 3 to 4.5? From 100 to 101.5? What does that mean? Yeah. Go ahead.
It's just from, it's not from 0 to 1.5 because it's just at that point, right? At this radius, that's the volume. But now we're saying we're going to look at it a different way and look at it in terms of accumulation. So yeah, so what change of 1.5 can we think of that as? Yeah, don't be afraid. Yeah, Dan.
Are you asking that if the radius changed 1.5, it would accumulate?
Yeah, but which change of 1.5? From 100 to 101.5? From 3 to 4.5? From 2 to 3.5? Those are all going to result in different amounts of accumulation. So the x value of 1.5 means, go ahead, from 0 to 1.5. From 0, so this means starting at 0, if we let the radius go up to 1.5, in that change, what will happen? So here's where the accumulation comes in. This is review. Tyler.
The volume will accumulate to 14.1372.
Yeah, so we'll have, as that change occurs from 0 to 1.5, we'll accumulate up to a volume of 14.1372. So rather than just thinking of it as the volume of the sphere, we can think of it as the accumulated volume of the sphere, little by little, as that radius increases from 0 to 1.5. So now we want a rate function out of this. First thing we did, what was the first thing we did to get a rate function? Okay, pick the delta x. And what do we do with the delta x? Piecewise linear function. Yeah, so diagonals. So let me pick 1.5. In my best drawing ability. That was, you know what it's supposed to be, right? Okay. The first two are pretty good. So this gave us some constant rates of change that trying to mimic what's going on, and what was the help of those constant rates of change?
What was the help of it?
Yeah, so what was the help of having that piecewise linear function?
Average rate of change.
Average rate of change. Yep, we can find the slopes of those constant rates. So here's maybe. Okay, that's the best I'm going to do. So that we could there we go. So what is this showing? Yeah, so these average rates of change are really just constant rates, right? So over here I'm showing the rate of change as constant rates. So this is building, this is kind of a simulation of the rate of change function for this, but we don't want a step function with big broad steps. We want a nice exact rate of change function. How are we going to get the exact rate of change function? That's the key. Tyler.
Make the delta x or the interval infinitesimally small.
Right, and so here's the beauty of graphing calculators. We can set these up, and then we can just grab delta x and make it small. And so this, as I make it smaller and smaller, the rate of change function starts to take shape. Can you still see it? Okay, so for very, very, very small delta x, we get this piecewise function will start to mimic the actual accumulation function very well, and then the corresponding step function will start to converge on a curve. Okay, so this is our rate function for volume of or y equals 4/3 pi x squared. Pi x, sorry, cubed. But there's one thing about this backward journey that's been different so far in terms of our ability to get this. So get this rate function from this accumulation function, and it's on the forward journey we could set up what kind of expression to get accumulation from rate. What kind of expression did we set up? Accumulation from rate. To get our exact accumulation function was what kind of expression? Integral, right? So, but that's all we had was just an integral expression. We didn't have we didn't really get to a closed form. That was an open form. We didn't get to a closed form of the accumulation from rate. But now we're seeing, if we start with accumulation and we're trying to find the rate function, we're finding out that it's possible to get closed form. Okay, and so the rate of change of volume with respect to x. Okay, and so what is the rate of change if the accumulation function is x cubed? So we've seen some examples. It's 3x squared, and we're going to see some more things today where if this is a constant, we actually just hold on to it. So that's actually, this goes over here now. So the rate of change of volume with respect to x, that x cubed, the rate of change is 3x squared, and we just hold on to the rest, 4/3 pi. And the 3 goes away, and what we have is 4 pi x squared. So if I were to come up here and graph 4 pi x squared, see that? Fits right on top of it. So that's where that step function is converging to as delta x gets very, very small for this rate function. It's converging to 4x squared. So in this journey back from accumulation to rate, we're seeing that, okay, so we know the process, but now there's an algebraic journey too, that we can just pretty quickly get a closed form for the rate function given the accumulation function. So that's what we're currently doing.
So
Yeah.
the rate function in
Yep.
this instance is the same. Is it the same, an identical graph to the accumulation function?
No, because this is they both curve up, but this one's 4/3 pi x cubed, which is a totally different graph than 4 pi x squared. They kind of both have that shape. No, but this is 4/3 pi x cubed. It's the accumulation function. This is 4 pi x squared. Totally different. Yeah, totally different. Okay, other questions? Okay, so let's talk about these rate of change functions. So let's talk notation first. I just introduced kind of a new notation, so let's formalize that. So if f is any function, and specifically an accumulation function, then we're going to use this notation, r sub f of x, to denote f's approximate rate of change function, the function who gives the average rate of change of f with respect to x over an interval of length h. So you all should be able to write what the rule is then for that function. See if you can do it. So r what is it? The approximate rate of change function that gives the average rate of change of f with respect to x over an interval of length h. Go, write it down. Everyone should be able to do it. We want the average rate of change of f with respect to x over an interval of length h. Have we learned anything? Can you do it without peeking? You got it? Cool, let's see. How many people think they got it? Not enough. So here's the key. So average rate of change. So the structure is average rate of change. What is average rate of change? In general, just in a general sense. How many people think they got it now? Raise your hands nice and high. Not enough. Okay, this is what we've been working on the last week. This is what we've been working on the last week. You're going to see it, and you're going to be like, oh, of course, yeah, I've seen that a million times. So, really got to know it forwards and backwards. Know it, recognize it if you see it, but then if you see a statement like this, it comes to your mind. So, one more time, who thinks they got it now? Oh, more, awesome. All right, so let's try, Richard, tell me.
You're asking for that f of x plus h one.
There's only one like this. You want to go for it? Yeah, that's a good start.
So f of x plus h
Uh-huh.
minus f of x over h.
What do you think? That's it. Okay, so this is our average rate of change function. Numerator means? Change in y. Denominator? Change in x, right? Get an average rate of change for a interval width of h. Okay, so reading it, we'll read it as the rate of change of the function f, okay? And so then in context, will this refer to the output of f or the input of f? The function value. Is that output or input? The function value. Output, right? That's our accumulating quantity. This is our accumulating quantity. So in context, you could say the rate of change of, say, distance, or the rate of change of volume, or the rate of change of profit. Okay, so that's our output quantity, our accumulation. So the rate of change of the function f with respect to the input x. That's how we'll read that. We're going to practice this language because we always want to attend to meaning, always attend to meaning, because we're going to be doing a lot of symbolic stuff now, but we don't want to lose sight of meaning. Okay? Okay, so let's just quickly go through this one you worked on for your homework. This one, x to the n. So x to the n, that's just a basic monomial term. And like we said, if that's an accumulation function, then not only do we know the process of building the rate function, but now there's an algebra to go with it, so we can get a closed form, instead of an open form, a closed form of the rate of change. Okay, so just here's some things. So when you have a binomial to a power, the higher the power, the more terms you have. And what happens in each of those terms? So look at what happens to the x for each term. So x to the fourth, then x cubed, all the way down to x to the first, and then what's the power of x here? 0. Okay? So our power of x marches down. What about the power of h? It goes up. So they go like this, right? So that's how these binomial expansions work. The one starts high and goes down to 0. The other starts at 0 and goes up to our power. So what will x to the n look like? The x power will start at n and march down to x to the 0. And the h power will start at 0, and with each term will march up to n. You see that? So we know that our f of x plus h is a key part of the average rate of change, so that's why we're putting that there. Okay, so if you ever want to find what the rate of change function is for something, you're going to start with what it is. Okay? Don't jump to the conclusion of the end, but so if it's the rate of change of f with respect to x, we know what that is. That's always this definition. It's always this average rate definition. Okay? So our f of x plus h, that's our x plus h to the n, which we just talked about. So we expand that out. X is marching down by 1, h is marching up by 1. So what's the first step then? What can we do to simplify? X to the n minus x to the n is? 0. Goes away. So we're just left with these terms. What's true about every one of those terms? They all have an h. So we can factor out an h from all of them. So here I'm showing that we're just going to isolate that first term. When you divide that first term by h, there's no longer an h. But all the rest of them, when you divide by h, there's still at least one h. And how do we get the exact rate of change function? H very, 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 very small. And so what will happen? All those will become insignificant, and we're left with this rule, n x to the n minus 1. So all of this is equal to the original rate of change function for f. So if f is this is our rate of change function for f. And you explore that in your homework. Questions on that derivation, which is understanding that's fair game for your quiz on Friday. Of course, every Friday. See, did I miss? Oh, sorry. Okay, so this is our first kind of closed form rule for rate of change functions. If your quantity function is x to the n, then the rate of change function is n times x to the n minus 1. Okay, what about constant functions? So we got one rule down. We got one rule. Let's just keep track of it up here. If r of f of x is x to the n, the rate is n x to the n minus 1. So this, oh sorry, this is f. Okay, so we'll keep a little, hopefully there'll be room over here to keep a little Roman tally. This is like a table, not division.
You're off the screen.
Yep, shoot. Better? Am I on there now? Oh yeah, I got it. Okay. So, constant functions. If an accumulation function never accumulates any changes in its value, so it never accumulates, it never builds up, it never deteriorates, it never ebbs away. What's its rate of change? How fast is it changing? It's not changing at all. So how fast is it changing? 0, right? 0. Okay, so let's show it mathematically. So how are we going to show it mathematically? First of all, how could we describe an accumulation function like this? It never increases in value or decreases in value. Therefore, that function must be equal to some constant value, right? So what does this function say about what to do with the input to get the output? What does this function say about what to do with input to get output?
No matter what the input is, the output's just a constant value.
Okay, what were you going to say? The input is the output. So we got two different things here. So the input is the output. Agree with that? No. So Adonijah, say it again.
That no matter what input you put in there, the output is always going to be that value C.
You see that? It doesn't really depend on the input. It's a function because you get output for input, but it doesn't care what the input is. It always spits out C. So no matter what the input is, output is C. Okay, keep that in mind. So that's what you should think when you see that function. Doesn't matter what the input is. I'm always going to get an output of C. That's a constant function. So no matter how we change x, we're not going to build up or ebb away because it's just going to stay that same constant value. So how do we show, what we want to show now is if our function is C, let's just write it down again. So if f of x is C, we're trying to show that the rate of change is what? It's never accumulating any value, or it's never deteriorating. So we're trying to show that. So what do we start with? So always start, we want to know what the rate of change with respect to x is. I'm going to start with that. So what will we do? So what's f of x plus h? C plus h. What does this tell me about this function again? So don't lose sight of what the function is. It's always C no matter what the input is. That's what that says. No matter what your input is, it's always C. So what's f of x plus h?
C.
What's f of x?
C.
What's the value of the rate? C minus z is 0, right? So it works. Make sense? Doesn't matter if you put in x plus h or x or a or x squared. It doesn't matter what your input is. 100, negative 100. You always get C. So if we follow our average rate of change function, we get 0 in the denominator. Because it's basically saying if you change the input, you'll never see a change in output, right? You'll never see a change in y. That's what that numerator is, the change in y. Okay, so we wrote that up here. If the function is c, rate of change is 0. Okay, next one. So next rule, constant multiple rule. At every moment in time, John has traveled 5 times as far as Mary. What can we conclude about John's speed relative to Mary's speed? What's that? Does it make sense that John's traveling 5 times as fast as Mary? Yeah, that makes sense, right? So at every moment in time, John's speed is 5 times as fast as Mary's speed. So we want to prove it. So, the problem is if I use the white, it'll white out that too. So we'll just see if it'll not be on top of anything. Okay, so John's total distance after X hours is F. Mary's total distance after X hours is G. So what statement using F and G says this? John has traveled 5 times as far as Mary. Can you set up a mathematical statement with the functions F and G that says John has traveled 5 times as far as Mary? What would that be? Anyone want to give it a shot? Yeah, Judith.
Is it f of x equals 5g of x?
She wants f of x equals 5g of x. Stanley likes it. Andrew, what do you think? If John has always traveled 5 times as far as Mary, does f equal 5 times g? Yeah, to make them equal, you're going to have to take Mary's distance and do what to it? Multiply by 5 to get them to be equal. That's right. Good job. Okay? So this conclusion now, at every moment in time, John's speed is 5 times Mary's speed. Can we write that symbolically? So the premise is he's going 5 times as far as her. So mathematically, how could we state that his speed is 5 times Mary's speed? Connor?
The rate of f of x.
Okay.
You know, kind of that r.
The rate.
Subscript f is equal to 5 times the rate of g.
Yeah, so the rate of change of distance of f with respect to x is equal to 5 times the rate of g with respect to x. Okay, so now, but this isn't proving that. This is just based on our intuition, right? We're just given this. We're saying this makes sense to be true based on our intuition. So can we prove it? Can we prove it to be true? Okay, so before we do that, before we prove it, let's look at some other notations for rate of change. So these are some other notations that you'll see, but they all mean the same thing. Okay, they all mean the same thing. We're going to read all of these as the rate of change of f with respect to x is 5 times the rate of change of g with respect to x. Okay, whether it's this one that we talked about earlier, or this one, this is called prime. Okay, so f prime, but we're not, don't read it that way. Don't read it as f prime. Read it as the rate of change of f with respect to x. Similarly, this notation right here. This is the rate of change of g with respect to x. So it's kind of like the more important something is, the more different names it gets. It's true. So the more important something is, the more names it gets. Okay. So rate of change function is it's the centerpiece of all of calculus. It's very important. So there ends up being several notations for the same thing. But we want to read them all the same way. Rate of change of f with respect to x, or rate of change of g with respect to x. So now, so here's just, so this is, in the previous example, it was talking about a specific example about the distance being 5 times as far. So this is just the general case now. The general case is that if one function is any constant multiple times another, then the rate of change is that same constant multiple of the other rate of change. So our next little rule here. If f of x is a constant times a function, then the rate of change of f is the constant times oops. What should I say? What should I put here? R of g of, right, the rate of change of g with respect to x. The rate of change of g with respect to x. Okay, so here we go. Here it is. So showing it mathematically. So what are we interested? What do we want to show? We want to show that this, the rate of change of f with respect to x, is equal to this. So how are we going to start? So this is the idea with proofs, okay? So here's the idea with proofs. If we want to prove that a equals z, are we going to start with the fact that a equals z? No, we can't, because we can't assume the thing we're trying to prove, or else there's no point to it, right? So we start by saying we're not sure, or we know it's true, but we can't assume it. So what does a proof look like? We're going to start with a, and we're going to do what? Based on knowledge of other things? Yeah, we can say a equals b. This is a known fact. And b is another known fact. It equals to c. And another known thing that we know. Whether this is algebra or things we've established in the past, we're using things we know. A is equal to b is equal to c. And we keep doing that until we get to z. And therefore, in the end, a equals z. This is just the basic idea of a proof. So what are we trying to prove? We're trying to prove that... Go way too much here. Right, so we want to prove something about this, right here. That's like our A. And this is like our Z. We want to prove, starting with that, we want to get to that. Okay, so what will our first step be? What do we know as a fact? Have we established that the rate of change of f with respect to x is? What can we say that it is?
A times x, a minus 1.
No, it's not. No, we don't know what kind of function it is. Yeah, we don't know that it's that kind of function. So what do we know? If we're starting with a here, and we're trying to get to z, well, we need to only start with a known fact about a, set it equal. So, Lauren, what do we know about the rate of change of f with respect to x? Yeah. Yeah. Is that what it equals? Always, right? Always. That's our definition of the rate of change of f with respect to x. It's our average rate of change definition. Okay? So now we're starting here, and we need to keep going with a string of inequality to try to make it to here. So that means we need to work on this. So if we know this, if f of x is c times g of x, then what's f of x plus h? What is it, Josh?
F of c of x plus h minus f of cg.
Okay, so just this part, just this much right here, f of x plus h. If f of x is c times g of x, then what is f of x plus h? C times g of x plus h. And what's f of x? Go, you do it. So you do the fun. See if you can do it. Remember, you're starting here. Our goal is to get to here. So a equals b equals c equals d equals our goal. And if we don't make any violations of rules or any jumps in conclusion, then we can prove it. So we got A equals B. So someone tell me what you got for C. Talia, did you get C? Equals?
I just said it was C of G of X plus H minus C of G of H, G of X over H.
Like that? Okay, so sometimes you look at it and you go, well, I don't know what to do with that, I don't know what to do, but then you look at your goal. So if you look at your goal, then it might give you an idea of what to do. Connor?
You can just pull out the factor of C.
Pull out the factor of C.
And then what you get is basically C times rate of G, because it's going to be, it's going to be G of X plus H minus G of X over H times, and that whole thing times C, therefore it's just C times rate of G of X.
So what he's saying is he pulled the C out. Now, do you recognize now what you got? What is that? Just got to think backwards now. You've got G of X plus H minus G of X over H. What's that?
The rate of G of X.
Isn't that the rate of change of G of X? And that's what we wanted, C times the rate of change of G. Oh, it's right under my thing. Well, actually, no, this is just now grouping it again. Just C times that ratio, C times the average rate there, which is C times the rate of change of G. So A equals B equals C equals D equals E equals F. Therefore,
A equals F.
A equals F. We never assumed it to be true, but we did all valid steps. We knew that was that, and we knew that was that, and we knew that was that. We knew that equaled that. We know that equals that. Therefore, the first equals the last. We didn't violate any rules, and we used all things we've established before. Okay? Sum. See if you can do this one on your own. So, sum of functions. What would be nice? So let's say, what would be nice if it was true? If the rate of change of k, if k was the sum of two functions, then what would be the most happy result? That the rate of change of k would be?
Sum of the rate of changes.
The sum of the rate of changes. That's what it is. See if you can prove it. Okay, that's what it is. See if you can do it. Okay, and if you get stuck, you can ask me, you can ask someone next to you, see if you can do this. Same principle, A equals B equals C equals D, you're moving towards what you're going for. It's a little bit harder, but you got the idea now. So you're just writing down, this is toward the end, right? So this is the kind of proof. So what are you going to start with? This side or this side? No, you're going to start with this side. It's A, right? To prove that A equals Z, you're going to start with A. You're going to work your way to Z.
G of X is the same thing.
You can only start with the left.
Yeah, G of X is the same thing as can't prove that.
No, you just jumped right to the end.
I know.
Yeah. So
That's
what
what
do you?
you're saying. Can't just jump to C.
Why can't
Judah,
you jump?
Judah, you can't go.
Because it's not a
C,
proof.
right?
It's not a
You can't
proof.
go B.
It's not a valid proof.
But have some
We
B and some C.
already know.
No, it's in B. Or
You too.
I know, that's why.
So
Because it's so adamant about it. Alright, so.
what does that equal? Regardless of this, forget about f plus g. What does that equal? Forget about f and g. So you guys are all, yeah, what everyone's doing is you're writing down the rate of change of this, and then you're writing down this as the rate of change, right? So you're going to start with the rate of change of k. What does that equal? Regardless of what k equals. What does the rate of change of k of x equal, regardless of what k equals? That's how you have to start. Oh, you did it too. You're all violating the rule. You're all violating this principle. If you're trying to prove that A equals Z, you're going to only start with A. What's that? It's not a constant rate of change. It's the rate of change of K. No, K. Rate of change of K. You're starting with the rate of change of K. What?
So, F plus H plus G minus
Why are you looking at that?
Because that's how I picked was trying.
Or anything like that? Everyone can copy the textbook down, Marcus.
I'm not copying, I'm just trying to see how it's over age.
Yeah, I'm glad they use different symbols.
F
The one that you
x plus H minus F of x
Mm-hmm.
plus G of
All right,
x
that's a good start.
minus G
Whoa.
of x.
Well, why are you stuck?
And then it's over H, so you can divide the H's of the plus sign between the two.
There you go. No, but that doesn't equal that. One thing at a time. What does that equal? You never wrote down what that equals. Show me.
So you have to do this plus H, so it's these. And then you put like terms together, and then the H can split. Right? Right? No, say it's right.
You anticipated too much.
Well, I don't know what else.
I mean, yeah, so eventually it's that, but it's not like you anticipated too much.
Still missing a couple of
So what does that equal? Forget about everything else.
tried to.
Oh yeah, right there. Yeah, what does that equal?
I know.
It's 2 times, so
So we're trying to figure out what the rate of change of k equals. Well, that's k of x plus h minus k of x over h. Isn't it? Is that jumping to conclusions, or is that a true statement?
true statement.
True statement. If it's the function's k, then here's our rate of change, average rate of change for k. So then, just do it one thing at a time. What's k of x plus h?
F of x plus h plus g of x plus h.
F of x plus h plus g of x plus h.
Minus f.
Okay? What is k of x? F of x plus g of x.
See all these stuff I missed. That's not fair.
So do you see? So that's valid, and then k of x plus h is our sum of our two with input x plus h. K of x is just the sum of the two. There, you can take it from there, right? So you're trying to get what many of you just wrote down from the start. Okay, so keep going from there, or is it time? It's time. So what's the general idea from here? What are we going to do?
Put terms together, separate them and put them on there.
Reorganize them.
Yeah, we're going to reorganize. We're going to gather together the f of x plus h and
Negative.
the negative f of x, because we're trying to get towards the rate of f. And then we're going to gather together x plus g of x plus h and g of x.
And then you can just separate.
And then you can separate them out. Yeah, I know. I wanted to leave our summary. So just gathering the f's together over h, gathering the g's together over h. What's this?
Right back.
The rate of f, right? The rate of change of f.
Rate of change of g. They're summed together. That's it. Yes, April, you had it.
You're uploading this right now.
You just kind of skipped the beginning. You just kind of jumped to the.
Okay. Like me.
All right, we'll see you on Friday. What's that? It takes me time. I got to export it, which takes time, and then I got to put it on YouTube. So this afternoon. This afternoon. We'll do it on Friday.
The Rock. I'm just telling you.
Yeah. Yeah. Homework due Friday.
And the quiz. Don't forget the quiz on Friday.
Hi. I didn't bring it with me. It's in my office.
I had it back there.
I am.
Can I bring it to you?
Yeah, if you want to meet me there in about 10 minutes, 15 minutes, or we can walk back together, it's fine.
What are you doing? I do that.
Does it make sense, Corey?
Yeah. So it's, I mean, I had, it was just going from,
So everyone started by writing this down, right? But you got to get there with legal steps.
when you put those steps in, I was kind of confused and I went to pop this back out, but it made sense. You just take it and separate it all.
Start with what is the rate of change of K? That's our definition. And take it one piece at a time. Don't try to think about the end. So what's that? Right? Some F and G with X plus H. And then what's that? Well, that's just the original. Then you rearrange it to get this. Hey, sir.
When it's talking about, I think it was proving the e to the x derivative, and it started off with like a 2 to the x and then a 3 to the x, and it showed like, it said the derivative as it moves from the right, approaching 0, and then also from the left. Like for 2 of x, it approached like the tangent line was 0.67 or something, and then for the 3 to the x, it was over 1.
Okay.
So when it's talking about approaching from the right, approaching from the left, is that like h is greater than? H would be positive, so H would be negative, and you would make it